Good morning. This is really going to be up to you guys, whatever questions you have. Have you been studying or are you going to start tonight? The personal question, sorry. hmm Number seven. Yes. That's like the hardest one on there. I kept it on there because I love that problem because it connects like solubility, like KSPs and the equilibrium constant and delta G is connected to the electrical potential, and it connects that to the line notation. I mean, it's like there's five or six different things in this problem, so it's a pretty long problem. It's one that I think is appropriate for homework, but yeah, this I think would be one of those that be pretty low probability on an exam for people to get through the whole thing because like I said, it's pretty drawn out. But I always include it on the homework because it took me a while to figure out. Whenever I first hit this problem, I was like, oh man, how is this even connected? So I'll walk you guys through it. First of all, what would you like? What's your first approach? You see this, and you're looking at KSP, but anyway, what do you see when you see this problem? The E, okay, yeah. Um, Before you can do that, though, you got to know what the half reactions are, right? And then how do you know from the from what you're given in the problem? How do you find the half reactions? Yeah, so you got to decipher the line notation. So here's the line notation slide right here. So this is, are y'all catching up? I see you're clicking around. Okay, this is the line notation slide. And so the very first thing you have to do is look at that and remember that everything's in alphabetical order. So you go up here and you see that silver on both ends. Well, the silver on the left is the anode, the silver on the right is the cathode. And that doesn't tell us much because they're both silver, but it does tell us about those reactions. And so the anode goes with oxidation and the cathode goes with reduction. So the first part, the silver bromide solid and bromide anion, that's part of the oxidation reaction. So the way I would write this out is I would say, okay, we've got an oxidation reaction and a reduction reaction. So let's draw the arrows first, and we'll remember oil rig. Okay. So if oxidation is lost, that means the electron is on the right side of the arrow. Yeah, you've got something, it loses an electron, so now that electron is apart from that something. And then reduction is gain, so it gains an electron. It might be multiple electrons, but we're gonna, start out with one. So this is like the very basics. We know that the first reaction is an oxidation, the second reaction in line notation is a reduction. So now let's build the rest of this out. And so we've got silver bromide solid, and then bromide aqueous. Okay. And so that's going to be the oxidation. So somehow we have to write this to where we have the electron on the right. So So we're going to have the bromide minus here plus silver solid, because that's the electrode here. So do you see that? Now what we've done is we've essentially stolen the electron from the silver solid. So this is 0 here, and then inside this compound we have a silver plus and a bromide minus. And that's an oxidation reaction because we're stealing that from the silver solid. So that's our oxidation reaction. So it's the oxidation of the electrode, the silver electrode, and then the bromide in solution is sticking to that electrode, growing a silver bromide solid film on there, and the electron is going through the circuit. Okay. Now let's do the reduction reaction. So over here we have a silver cation and silver, and so we can write the silver cation with this electron because it gains an electron. And let's go ahead and put aqueous on our little bromide. Okay. And then this is gaining an electron, so it becomes silver solid. So this is happening at the other side. So the other electrode over on the cathode, the one on the right in my imagination, is having electrons come through the circuit, and it's got silver ions in solution. And so the silver ions are migrated towards that cathode. The cations are attracted to the cathode because the cathode is negative, and it grabs that electron and plates out on that electrode. So that electrode's getting heavier with silver. The anode is getting heavier because it's gaining silver bromide. And so bromide is sticking to that electrode and making it silver bromide. And so then we would balance the electrons if we needed to, but we don't need to because there's one on each side. And then we can write this out. Okay. So what I'll do is I'll write the whole thing out, and then I'll cancel the silver. Well, I guess I could cancel the silvers now. We can cancel the electrons. So do you see how this produces an electron and it consumes an electron? So the electrons are gone. And this consumes a silver solid on this side and produces a silver solid on that side. So the silver solid is gone. And so we have this net reaction, Ag plus aqueous plus Br minus aqueous gives AgBr solid. And the way this is connected to the KSP, you see that the KSP reaction is the reverse of this. You know, if you're doing a solubility of silver bromide in water, silver bromide is a precipitate, it's not soluble. The KSP experiments are always call them the solubility of insoluble things, right? Because nature hates zeros. So you put silver bromide in solution, some of that silver, just by entropy, is going to end up out in solution, okay? But this is sort of the reverse of that reaction. So this is going to be the equivalent to 1 over KSP, because KSP is for this reaction, AgBr solid going to Ag plus Br minus. So that's how it's related to KSP. So if we can find the voltage for this particular cell, then we can find the equilibrium constant, then we can invert that. 1 divided by that equilibrium constant will give us KSP. Does that make sense? So that's the pathway. So let's figure out the voltage of this cell. So let's just make a column right here. So this first one, if we can find this in a reduction potential table, we see it right here, written as a reduction. So we have the reverse of this reaction right here. So we're gonna change the sign on that one. So negative 0.07. See how we change the sign on that one? Okay, and then let's find the silver reduction. So that's the first reaction in this table. And it's written as a reduction up here, so we don't change the sign on that one. So that's a plus 0.8. Okay, so we got 80 minus 7. So what is that, 73? So it's a plus 0.73 volts. So that's the cell potential for this. If we have 1 molar solutions of silver bromide, that's what the cell potential would produce. Okay. So the delta G for this is the number of electrons times Faraday's constant times the cell potential. Okay, and the negative sign too. So minus, and then we have 1 mole of electrons. Do you remember Faraday's constant? Yeah, 96485 volts. Let's see, joules per mole, right? Is that correct? Joules per mole. So the mole of electrons is gone, and the volts will be canceled. No, is it joules per mole volt? We have to cancel the volts, so the volts is in the denominator. And then we have the plus 0.73 volts. Yeah. Break out the calculators. So it's 70,434 joules. That's the delta G for this reaction. Okay, so then we can find K for this reaction. Do you remember the equation for K? Mm-hmm. Just that exponential, right? So it's E, it's like the Boltzmann distribution, right? The energy difference though is the delta G over RT. And we could say joules per mole just because it was for like 1 mole of silver bromide or whatever. That'll help us cancel the per mole and the R, and the gas constant. Okay. Do this at 298. Yes. Yeah, there he is. Thank you. Very good. I'll get you a sticker. 'Cause that is a always a danger, and whenever someone points out a mistake I make, they get to pick from the sticker sheet. It's always a danger of dropping the negatives on these things. And so it's a minus a negative, right? So now that we have a positive. All right, good. Thank you. And that would make sense because it really wants to be the precipitate. So it's going to be a very positive equilibrium constant. So, so, so it's 2.2 times 10 to the 12th, and that's equal to K, which is also equal to 1 over KSP. So we can solve for KSP now. So it's 4.5 times 10 to the minus 13. And we're close enough that would have triggered, that would have been counted correct. But what a great problem. We have to understand line notation. We got to figure out the half reactions, and we got to balance the electrons if needed. Find the net reaction, find the E cell. Then once we have the electrical potential for that reaction, that galvanic cell, then we could find the delta G. And then once we know delta G, we can get the equilibrium constant. And then once we recognize that that reaction is actually the opposite direction of the KSP experiment, then we can invert that equilibrium constant and get the KSP. I mean, it seems to me like a very easy way to measure KSPs because what you're dealing with KSPs is, you know, electrochemical, cells are pretty easy to construct, and you know, you get a potentiometer and you measure the potential of that reaction, and so this is it's a good way. Electrochemistry is a good way to get delta G's. That's all I'm say. Yeah. Okay, so that's that problem. This is the work I did last year, same problem, but I think this much cleaner this year. You can decide. For the specs for one polar, the reactions for CHEM thing, and then like a fourth one is a little bit earlier. Okay. Yeah, up here. Yeah. Should be the Nernst equation, right? Hmm. Yeah. So you did the natural log version, RT over NF, ln Q, right? Yeah. It's just the natural log form of the Nernst equation, so we can do that. It gives us E cell, so that's easy, plus 0.63 volts minus 8.314 joules per mole Kelvin. This is a pretty easy one to balance with the number of electrons because we've got two electrons switching from the lead or from the zinc to the lead. So zinc's being oxidized, lead's being reduced. They're trading two electrons. So we have 2 moles here of electrons. And then we have the, let's see, Faraday's constant, 96485. Good morning. Joules per mole volt. Joules per mole. It doesn't look like, I guess we just put the number of electrons on there, not the moles, because then otherwise we have another unit of moles in there. So it looks like we're just using the unit. Okay. And then we have the, oh yeah, temperature, 298 Kelvin. And then products over reactants. So the zinc is 1. And the lead is 2 times 10 minus 4. So we're really kind of pushing this reaction backwards. Let me just see, 0.63 volts minus, I'm just going to do this front piece. I'm going to do this in parts. Yeah, yeah. So yeah, that's where it went, that's where you went wrong. Yeah. So that 0.059 or whatever, that's for the, when we did the log base. So that front piece would be, have a factor of 2.303 in it. Yeah. So this piece is 0.0128 times the natural log of that concentration. So 2, yeah, so I got that. I got the answer. So that was it. You found your error. And it's always good to see if it makes sense, right? So what we're doing is we're adjusting the voltage down. Remember, delta G is equal to minus NFE. So as E goes up in volts, delta G goes down, meaning it's more negative, more spontaneous. So a positive cell is more spontaneous, and more negative delta G is spontaneous. They have the opposite sign of each other. And we're adjusting this down. So what we're doing is we're reducing the cell potential. So we're making it less spontaneous. Does that make sense? Yeah, look here. This is the reactants. We've got very little reactants, and we've got the standard amount of products. So we're already running out of reactants, and so it's less spontaneous. So we're adjusting that voltage down. So that's sort of the mental check you want to do to say, should the cell potential be higher or lower in this situation? It should be lower than 0.63. 0.63 is what you get with all the concentrations are 1 molar. So your Q would be 1, and the log of 1 is 0, and there's no adjustment. So if everything in your concentrations is is 1, then you're going to have a 0 adjustment. Why don't we include the solids? Yeah, that's right. So we're dealing with the aqueous concentrations, or I like to say the concentrations that can change. So as long as there's some solid, then you can get equilibrium. If you run out of solid, you can't get to equilibrium. But if you have some solid present, wherever there's solids, um, that that would be essentially the concentration of that solid in the solid. And the liquid, like liquid water, would be the concentration of water in water. So it's not going to change either. So it's only the ones that can change, the aqueous ones. Now, where do other concentrations go? Well, they're lumped into the constant. So part of the reason that constant has the value it has is because of our convention. We're picking only those concentrations that can change, and we're just leaving the others in the constant. They're all lumped in there. Mm-hmm. Mm-hmm. Yeah, so this is let's see, there's the rules, and these are the rules for balancing your redox reactions. But if let's see, so there is a step 5. So let's see if I can write it on here. So 5. Mess up. If in basic conditions, um, so we'll have this, it will add hydroxides to cancel all the H pluses, but you can't do anything on one side. You have to do it on both sides. So let's see if we can find one. Um, well, we can balance that one on the homework. So we've got Cn. So our two half reactions would be Cn minus gives us CnO minus. So we've balanced the carbon and the nitrogen. Now we have the oxygen. So we're going to add water to this side. I should make y'all tell me what to do. Okay, so I've added the water. Now what's the next step? Then we just added hydrogens to a reaction that didn't have them. So now we got to balance those. Where do we put them? How do we do that? Put them on the right, and we add H pluses, right? And then we add the electrons. So on the right-hand side, we have 0 charge. On the left-hand side, we have -1. What? 2 electrons? Oh, we got 2 hydrogens. Yeah. Okay, so we got a plus over here on the right. +1 on the right, -1 on the left. So we need to add 2 electrons to the right-hand side. Everybody agree with that? Okay, good. All right, so that's our first half reaction. Let's do the iron. Iron should be easy. Okay, we got a +3 on the left, a +2 on the right. We can reduce the +3 down by adding an electron. And so that's a reduction. We're reducing the iron. Then we're going to match the electrons and add everything down. So on this one, we're going to multiply everything by 2. 2 electrons, 2 iron 3s, 2 iron 2s. And then we'll cancel the electrons. We've got the handshaking all taken care of. And so then we have H2O plus Cn minus plus 2 Fes is CNO minus plus 2H plus 2Fe 2 plus. Just barely fit it in there. Okay. So we have this situation, and now if you look at that, we're producing acid. And so this reaction is not going to go very well in acidic solution. So since the protons are on the right, we need to really change the conditions and see how would this reaction behave or react if it was in basic solution. A basic solution would drive this reaction forward by consuming those acid protons. So we can do that on paper by saying, well, we've got 2H pluses here. So what we're going to do is we're going to add 2 hydroxides to the right and to the left. Okay. And that's going to produce a water on the right, or it's going to produce 2 waters. Okay. I'm doing this kind of in 2 steps, all on one line. So here, this produced 2 waters, right? And we've got a water on the left and 2 waters on the right, and that's redundant. We don't need that. So we're going to cancel one of these here. We're going to get rid of that 2, and we're going to wipe this water out. Does everybody follow that? We just did 2 steps. We neutralized the acid by adding hydroxide to both sides. And then we're going to end up with 2 waters on the right and 1 water on the left. We don't need that. So we're going to get rid of one of those waters. And so this is what we end up with. So 2 hydroxides. So this is the basic conditions. We just have 1 water and then the 2 irons. And of course, everything will be aqueous except the water. The water would be liquid. So I'm just going to put liquid by the water. And so you could have answered this question correctly without really knowing how to do the full problem. You could have said, well, I see that the electrons are going to have to match, so that there should be a coefficient of 2 in front of the Fe3 plus. But this is how you do it. You neutralize the acid with the hydroxide, and then you're going to end up with waters on both sides, and so then you get down to having waters only on one side. Cool. What about some of the topics that y'all covered on your own, like the activity coefficients and Debye-Huckel equation and ionic strength? Y'all okay with those? But see, it's a different Huckel. Yeah, that's dealing with the molecular orbitals, and this is the Debye-Huckel equation. Huckel. I like Huckel because it reminds me of Richard Scarry, Huckel the cat. I don't know if y'all know Huckel the cat. Let's see, it's down here at the end. Yeah, this equation here. It's probably the same guy. Yeah. It's all very dependent on that ionic strength. And essentially what happens in the solution is the more ions you get into solution, the easier it is to dissolve ions. So if you think about what's going on when ions, like our silver bromide solid, when it breaks apart, you have silver ions and bromide in solution. And this is, they would prefer to be precipitated. They prefer to be, the insoluble silver bromide. So as soon as a silver and a bromine get out into the solution, it's pretty easy for them to find each other in DI water. You got deionized water, and that silver feels a negative charge somewhere, and the positive and negatives attract. So it's going to find that bromide and crash back out. Okay. Or it's going to be attracted to the precipitate, because let's say 2 bromides left and only 1 silver, then well, say two silvers left and only 1 bromide, then this solid is kind of charged negative. So it's going to find that solid and go snap back to it. But if I have, say, sodium chloride in that solution, now I've got a silver in solution, and it's all it looks around and all it sees is chloride. It's pretty happy, you know, or maybe let me say nitrate, because silver nitrate's not insoluble. So if I had silver chloride, it would precipitate too. So let's say I had sodium nitrate in solution and silver bromide as a precipitate. And as silver gets out into that solution surrounded by nitrates, and it doesn't want to precipitate with them. So the solubility of that silver bromide, which is a precipitate, it should not be soluble, is stabilized when you have a non-interesting salt. Like it's not interested in reacting with the sodium nitrate, but that salt that doesn't participate in the reaction at all stabilizes the aqueous solution. So the silver can be happy around all those nitrates and it doesn't precipitate out. So you can actually increase the solubility of silver bromide or silver chloride if you have like sodium nitrate in solution. It doesn't react with it at all, but it stabilizes the aqueous solution. So that's what's going on with the Debye-Huckel equation, is we can calculate these coefficients that they go in front of the concentration. So you might have KSP equal to silver, let's use our example, silver bromide. These coefficients go in front of it. So you have the thermodynamic, I'll just call that thermo, is equal to these coefficients like gamma AG, gamma BR. I'll put them in front, actually, just to show you there's kind of like a correction term. So gamma AG in front of AG's concentration, and gamma BR in front of the bromide concentration. So that's what we're doing. It's like these activity coefficients are adjusting the concentration values. And so if you have this activity coefficient that's, you know, say much less than 1, then your silver concentration is going to go up. So that the thermodynamic equilibrium stays the same. So if the coefficient is less than 1, then the concentration is going up. Did I have any homeworks on this? This is the last part of the course, but I didn't know if I had any homeworks on this. I don't know why it's in this set of review slides, but we'll get to that. How'd the viscosity lab go? What was that? The number 50? It wouldn't go through the capillary? Oh, great. Okay. So did it take forever? How long? 6 minutes? Yeah, it's pretty long, but it's not impossible. You have very accurate times, unless you fall asleep. Yeah. Okay. So we need to figure out a way to clean that out. That's the problem with these, is that capillary, if there's any precipitate, if it dries out, somebody didn't clean it well, that's probably what happened. Um, Even if you have a tiny little particle in there, what's it going to do to the flow? What radius to the 4th power? So if you shrink that capillary, then you could have a really inaccurate viscometer. The the number 25, 50, 75, 100, those are related to that capillary diameter. And so we could figure out, you know, somewhere on that spec sheet, it'll tell you what that radius is for that capillary. Is that what you're asking?
Yeah, because I was just trying to like calculate from our data the viscosity,
Yeah.
but I wasn't sure what the height or the radius was.
Well, you don't need to use those. So if you look at this equation, all of this stuff is captured right here, right? And then that just becomes K. So you should measure water because you know water's viscosity and density. And so you solve for K. So you standardize it. So K is equal to water's known viscosity and its known density and the delta T. So so you measure this for water, delta T, and you can solve for K. And then you use that K to do your unknown solutions with the same viscometer, right? You gotta, yeah, obviously. So you'd got to do water in all of the viscometers, or some standard solution like a high purity oil. So, like say, if you wanted something that water was just too fast in because it's not very viscous, and maybe you have to use a standard oil that's well refined, filtered, and so on. Um, and you know its viscometry very well, or viscosity very well. Then you could do a viscometer constant for that oil, and you get it and get that viscometer calibrated, if you will, and then you could use it on other oils that were less than. So you could do that. Let's say you had one of these faster viscometers, one for more viscous liquids. Um, you could like use fresh motor oil, you know, and you've got a viscosity measurement on that motor oil, um, and then you could take really old and worn out motor oil and see what the viscosity change was. So you could do fresh versus aged and see, they say viscosity breakdown. You break down the molecules, they're smaller, they have less viscosity, so they don't lubricate the engine as well. And so you could see the viscosity breakdown perhaps. I've never tried that, but that would be one option. I've often wondered if I could do this in like a funnel, like on our tensiometer. We have that mass measurement, and so if you could have that funnel, it's a nice geometric shape, and then you've got the capillary that flows out of the bottom of the funnel. If I could suspend that from our balance, you could squirt in some liquid, and that would cause the mass to go up, and then it would drain out through that hole, and the mass loss would be related to the flow. And I think that would be a nice, easy viscometry measurement. So you could have, our tensiometer, we could have the balance on there collecting data, and you squirt some water or some liquid into a funnel. Of course, the funnel capillary is way too big, but that you would see this mass curve change. It gets lighter and lighter and lighter at a certain rate. And you could easily get into Excel and calculate that rate and see what the viscosity was. So never done that, but that'd be a fun research project. Try to figure out how we could use that underhook balance to measure viscosity. But that's not on the test. So. Be prepared to use this Poiseuille's law in any different way I want to make it. Like, let's say I give you the viscosity and the diameter of the pipe, and I want a particular flow rate. What kind of pressure do you need to use? So, so that would be, again, solving for a different variable, but using that equation. You should be able to solve for P2, given the flow rate, given the viscosity, given the diameter of the pipe. That's how they control oil and gas, by changing the pressure of the mud that they put into the. So they're drilling a hole into a pressurized um, reservoir of natural gas or oil. It's going to shoot out as soon as they poke a hole in it. Here it comes, and you've seen blowouts like, maybe spindle top. You see the oil shooting out of the top of the derrick, or you have a blowout natural gas. You hit a big pocket of natural gas. Here it comes. And so they put really dense, heavy, like bromide and iodide salts, mud in that column as they drill down. So it's, thousands of pounds of mud pressure keeping the oil and gas down in the hole. So so they're playing with P1 and P2 to keep that flow rate to zero, or actually negative. They want the mud to flow down into the pipe and clear out those chips. So sometimes they take risks. They lighten the mud a little bit so that, say, natural gas can leak out while they're drilling, and they produce while they're drilling. So that's, if they capture that natural gas, they can sell it and they can make a little money while they're doing the drilling part. But it's a really tricky balancing act, because let's say they hit a higher pressure pocket and then they can get a blowout. So Poiseuille's law can be applied to oil and gas pretty well. It's up to you guys. What's next? Number two, they're actually doing helium. There's designs for reactors that use helium to cool the reactor core rather than uh, liquid water or steam. I had where is it? Right here. So air is pretty bad. Vacuum is the best insulator, the worst conductor of heat. Air is still pretty bad. Um, Here's helium, 0.1. And water's about, liquid water at room temperature is, 5 or 6 times more conductive than helium gas. Helium's not great, but you could pressurize it. It's like helium and plywood are pretty close to each other. I wouldn't want to make a nuclear reactor out of plywood, a particle board. Uh-huh. Yeah, it's really low. It's that number. I just look at that number though, and I doubt it. That just can't be. I mean, but I hear about that too. They put those things around it, and also they're radiative, so they try to reflect the infrared back into your body, because you're giving off infrared light too. They made kind of a mylar. They, I don't know if this was successful, but they made like a mylar camouflage. Um, in the Ukrainian conflict for thermal scopes, and so they're looking for hot bodies, and so they have a really smooth camo. It's got a camo pattern for if it's daytime, but they're kind of hiding behind a mylar poncho, and it's preventing their body heat from shining out and being seen by thermal imaging. We have a thermal camera that we drive around the woods with, looking for rabbits and armadillos and stuff. And I mean, it's just not even fair. You can see them for hundreds feet away, maybe yards. You can see them a long way off. See a hot spot, and then you get closer. And we've got a kind of a cheap one. We've got like a little um, low res uh, hot spot. I mean, a thermal scope. I went by one of the gun shops and looked at thermal scopes to see, how good they are, like the best ones. And this one I was using, I could see the studs in the wall. I could see the different heat signatures from the studs in the wall, so I could see through the sheetrock. And then he said, now try this one. It's higher resolution. And I looked and he said, look at the studs carefully. And you could see the nails or screws that they screwed the drywall in with. It was that high resolution. Yeah, it was incredible.
That's cool.
Yeah, that's right. I couldn't see through the wall, but I could see I could see through the drywall. What I'm seeing is the differential heat of the surface of the drywall because of the differential heat transfer through the 2x4 or the insulation. So the insulation was darker, the 2x4s were brighter, so they're hotter. And so the wood of the stud was bringing heat in from the outside, and so I could see them on the inside of the room. Wasn't that I was actually seeing through the wall. I was seeing the surface heat differences where it was connected to a screw or a stud or insulated backing. But those are really useful. You can walk around your house and find your heat leaks or your code leaks. And so home inspectors are buying them because they can walk around the house and see how the insulation is and stuff. So that's thermal conductivity. Freon. Okay, yeah, so that's again, it's kind of like Teflon, it's a brand name. So Freon is a bunch of different um, molecules that are chlorofluorocarbons. So Cl, F, and C. And so there's a bunch of different ones, and they all have different numbers. But like you could do, and I don't know which ones they are because it's kind of confusing. But like if you had CF, Cl3, or CF2, Cl2, these are all freons. So the reason they banned them is because they're very inert, and that sounds great for us. So they were really good solvents. They're non-flammable, so we could just, they were just like spraying down the floors with this stuff, and really clean labs, like clean rooms and so on. They could clean with Freon like crazy, and it wouldn't really harm the workers. Toxin is the dose, though, so probably a bad practice to just mop the floor with it. But anyway, it was going, because it was inert and didn't react with oxygen, it got up in above the troposphere and into the stratosphere where ozone is, and the UV light would split it apart and make chloride or chloral radicals, so Cl dot. Okay, so basically chlorine atoms, and those would react with oxygen and form ClO dot, and this reaction would catalytically destroy ozone. And I can't throw the reactions together real quick, but it would react with ozone to produce oxygen and another oxygen that would react with the chlorine and become ClO, and so it would just reproduce itself. So once these molecules got up into this stratosphere, then they started destroying ozone. So they banned them and got rid of other ozone depleting chemicals, and the ozone holes repaired itself. So this is like the best example of a global effort to do something, for the environment. And that's also why I think a lot of the climate regulations are garbage, because they're not really addressing the problem on a global scale. They're exempting whole countries that produce tons and tons of CO2. So if it really was a global problem, they put a global ban. They would take a hard approach with it. They're not. It's a money grab. And so that's all I'll say about that. I don't want to get too political, but the thing is, this was an example of a successful global effort to tackle an environmental problem. And the climate warming or climate and global warming thing, their response is characteristically totally different. And so that's why I was like, no, if you're exempting countries from it and you're playing games and you want to have a climate fund that's going to take in tons and tons of money, they didn't do that for this. They just said, no, we're not going to produce any more freons. So what they do to this is they'll put a hydrogen in there, so that this one is okay. So CHFCl2, that's not a freon because it has a hydrogen. So hydrofluorocarbons are okay. They react with oxygen in the troposphere and they don't make it to the stratosphere. So they'll react with oxygen, they'll produce another reactive species that gets reacted and rained out and kept down at the surface level of the earth. And so that's good. They'll put double bonds in there, which are very reactive. So we've made a ton of new solvents and new refrigerants. So when they're changing out the refrigerant at your house and there's a little escape when they hook this thing up or break a line, that gets released to the environment, and those little releases add up. But if it's something reactive to oxygen, then it doesn't get up to the stratosphere. It doesn't, because those hydrofluorocarbons would also catalytically destroy ozone if the chloride got up there or the fluoride got up there. But if it reacts at the surface level with oxygen, then it's not going to make it up there. So that's all the new refrigerants. They're much more expensive for some reason. And so that's why sometimes if you've got a large air conditioning unit, it's cheaper to buy a new unit that's made for a new refrigerant than it is to refill the refrigerant. So we have our church has a big gym, and it was going to be like $17,000 to refill it with refrigerant, and that's about the cost of a new unit. So they said, we'll just get you a new unit. So crazy. Yeah. Mm-hmm. Mm-hmm. It's very cool. Yeah. Yeah. But did I say anything like off base? Is it pretty similar? Yeah, yeah. But if there's a hydrogen in there, then it's better. I don't know that it's perfect, but it's better. Yeah. There's probably never a perfect. Yeah. Oh gosh, 8:57. Nobody's out there.